thank you all for being here and welcome. I am Siddhant, developer advocate at neptune.ai. So at Neptune, we are building the world's most scalable experiment tracker for teams training models at large scale. And by large scale, what I refer to is like, say, retraining your own foundation model scale. So in my day-to-day, like say work at Neptune, I interact with such teams on a daily basis, learn their challenges, suggest solutions. And over the next 50 minutes or so, I will be sharing some of those challenges and solutions with you so that you kind of get a head start in what you're doing in your, say, large scale training. So yeah, let's get started. So first, like the very basic question, like why do you even need to monitor your experimentation, right? What's the need to like check how your experiment is progressing? So apart from the very basic and generic reason, like to measure and track experiment progress, there are four major reasons that there are four major groups of reasons why you should monitor your ML experiments. So, and when I talk about monitoring, I'm not referring to just sitting in front of your screen and checking your, say, PyTorch console logs, although that is also a form of monitoring, if you may. So, why monitor? So, first, live monitoring. You see the experiment progress as it happens without having to wait for the checkpoints to end. So, you're able to see the exact, like say, step your training is on and be able to take corrective action as and when it is needed. Second, it's an automated process, right? It's a one-time setup. So you set up your monitoring pipeline and then you can reuse it for different kinds of experiments. It's generally like say framework and platform agnostic. So set up your monitoring workflow once and it works out of the box for all similar experiments, letting you compare experiments, analyze results and debug issues. Third, it gives you a single source of truth. So all your experiment metadata is logged to one common place. So you don't have to like say go to Git to check your source code, go to S3 to check for your data sets that was used, or worse, check that Jupyter notebook sent by that collaborator in say email or Slack. So like you get a common place where your code, your data sets, your model configurations, Java parameters, all of them are logged, and it's like say easy for you to access and anyone in your team to collaborate with. And finally, like all of this basically leads to better collaboration, right? Since everything is logged to a shared dashboard and not hosted on your local system, everyone can see what others are doing and access the results programmatically. So like say if you have a distributed team, like your different teammates from different geographies can access your results, compare experiments, and like say maybe suggest improvements or debug issues. So over the course of the next now 45 minutes, we shall discuss some of the challenges in the say field of say live monitoring, visualizing and comparing results, reproducibility and transparency when working with large scale models. We shall also discuss, like I mentioned, some of the unsolved challenges in this space, and some of these challenges are very generic, can be applied to like most of our use cases, and some of them are say very specific, will be applicable to only a small say niche. Maybe you can resonate with some of them, or better yet, maybe if you're working on solutions of some of those unsolved challenges. And like I mentioned, if you are, we would love to get in touch. Finally, we'll have a Q&A at the end, and we would love to also hear about some of the challenges that you are facing and those that we might not have touched upon during the session. Cool. So first, live monitoring. And when I say live monitoring, I refer to say true real-time live monitoring, not say batch monitoring or micro batch monitoring. So live monitoring is important because it lets you take corrective action as soon as an incident occurs. And why is this especially important at scale? So large scale training can involve, can cost say hundreds of thousands of dollars just in infra costs, right? Any delay in corrective action means that you are spending thousands of dollars into infra that's not really doing anything, or worse, it's doing something that you don't want it to do. I mean, imagine paying for 200 A100s for a module that's divergent. No. Yeah. So even though like live monitoring is so important at this scale, like I mentioned, true live monitoring is still a challenge, mostly because of the data volumes and the throughput rates required. So hyperscale training might have a data throughput of 100,000 of even say million data points per second. Most monitoring tools just don't handle this scale of ingestion, leading you to either leading to either your training lagging because your training is now waiting for your monitoring tool to sync sync its backlog. Uh, uh, this basically creates a bottleneck by the tracking tool, or you start seeing delayed tracking metrics. So, for example, you might be seeing results for the 200th epoch when your experiment is actually has progressed past the 400th epoch. Now, one kind of a solution that some teams use is they batch their monitoring calls. So, for example, what they would do is instead of say logging results at the end of every step of or every epoch, they would batch it and aggregate metrics, log it at the end of every 100th step or 100th epoch. So this is not the true live monitoring I'm referring to, because what it does is it introduces two issues. One, your code becomes more complex because in addition to your training boilerplate, you also have to like say handle the aggregation of metrics at each batch and then log it at the end of each batch. And this also like say introduces like say you have to spend more resources uh, when those resources could be used towards actual training and not really like dealing with a slow experiment tracker or a monitoring tool. And then this also adds a bit of lag to your, say, monitoring. Because, say, for example, if you are batching at the end of, say, every 100 epochs, if your experiment is currently at the 250th epoch, just an example, and something goes wrong, you don't have visibility into the last 50 epochs because the last metrics you had logged were at the 200th epoch. So if something goes wrong, debugging is a pain because you don't really know what has happened in the between the last batch log and the current state of the experiment. So this brings us to another challenge, which I think all of you might have faced when training models at any scale: hardware failures, right? So distributed systems have failures, and as Bandish says, the rule of thumb is one failure every 1,000 GPU days. And 1,000 GPUs is generally like pretty common now when you're training your own foundation model. So like this basically translates to one failure every day. Now, the problem with hardware failures is, as Davis from Mosaic ML and now Databricks says, whenever you get a hardware failure, you don't get a hardware failure exception with the root cause of action and recommended solutions, right? So, like Davis says, uh, your job maybe completely crashes, maybe some of your nodes slow down a bit, or you could even start getting incorrect outputs. It's up to you to figure out what went wrong and then how to correct it. Now, there's live hardware monitoring is not really a solution for this, but it can really help you debug what went wrong. So, for example, it can like help you elevate the impact of your say of a hardware failure. So live monitoring of resource utilization is pretty hard, especially without boilerplate code. I mean, you have say libraries like PSUtil that help you capture system metrics and log wherever you want, but that involved a lot of boilerplate code, which you would rather use to training your model, not really monitoring the resources. Most training frameworks don't handle this out of the box, but most experiment trackers actually do. So while this does not solve the problem of hardware failures, it makes it easier to debug and find the root cause. So for example, seeing how the memory increases. So the chart on the top right, it's basically the memory consumption chart. Seeing how that increases can help you debug out of memory errors, or at least predict if you might be if you have a risk of running out of memory. And similarly, it also helps you identify bottlenecks in performance. So are you being limited by your GPU capacity? Are you being limited by memory? Or are you being limited by network bandwidth? So all of this is like easily measurable and quantifiable. If you're able to see all of these in real time live, it's a lot easier for you to be able to like find what the actual bottleneck is. So like James mentioned, right? Seeing live memory consumption like can really help you debug out of memory errors. And as Vostok mentions, utilization graphs in dashboard are a perfect proxy for finding some bottlenecks in performance. So the graph on the bottom is basically like your GPU utilization. Now, coming to another solution that can help cut losses when something goes wrong. So for example, like you see your loss curves decreasing, and then at a particular time, they suddenly start increasing, right? I mean, you run into some issues. So at that point, you basically have two courses of action. What you could do is you could pray and let the experiment continue and hope that your losses start decreasing further. Or what you can do is you can cut down your losses, stop your experiment, and then try to debug the issue. But if your experiment is like say running on a cloud provider, getting that loss curve might be a bit of a challenge if you're accessing only cloud infra oriented logs. So for example, if you are trying to access CloudWatch logs. So, and even if you are able to get something of a loss curve, it might be difficult for you to, like, say, remotely stop the experiment without having to, like, say, log into your cloud console or SSHing into your server where experiment is being run. Now, a very frequently overlooked feature of most experiment trackers is the ability to remotely stop experiments. So you can actually stop the experiment from the experiment tracker dashboard itself. So the same interface where you are seeing your loss curve, you can also, like, stop the experiment from that very same interface. So basically, like, what happens is if you see something going wrong, you can effectively early stop your experiment, and then, like, you don't have to pay for infra that you don't really need. Now, this also saves time because you don't have to wait for the experiment to complete. But for the most savings, you should have checkpointing. Now, use checkpoints at, say, frequent intervals. You don't have to restart from scratch. So remote stopping won't really help if you stop and then you have to restart from scratch again, right? So stop your experiment, revert to the previous checkpoint, change something, and start your experiment. Now, most mature training frameworks already offer automated checkpointing and warm starts from the previous checkpoint, but most of these by default save the checkpoints to the same machine. Right. This does not help if, say, hardware crashes, or for example, you are using spot instances and then they're reassigned, so you lose all your data. Right. So for maximum resilience, the checkpoints should be linked to your monitoring tool or experiment tracker. So some like some training frameworks let you specify where your checkpoint should be uploaded. So for example, I think Lightning lets you specify the S3 bucket where you want your checkpoints to be uploaded, right? But how do you then link that remote checkpoint to the current state of your experiment? So this is where you should use a, say, tracker that helps you like remotely link the artifact basically. So in this case, if your checkpoints are on S3, you could actually link the URI of the checkpoint on S3 to a particular step. So you know at each step or at each interval which was the last checkpoint or which was the checkpoint which is logged at that particular step or interval. Now, what you could also do is, some of our self-hosted customers do this. You could also upload your entire checkpoints to the experiment tracker itself, and that, like, gives, again, as mentioned earlier, the single source of truth dashboard, wherein you have, like, all your experiment metrics, your code, your parameters, your checkpoints all in one place, and you can, like, easily revert from the last point of failure. Now, however, there are two caveats to successfully restarting an experiment from a checkpoint. One, you have to assume that the experimentation environment is constant or at least reproducibility. So if your environment changes between your last checkpoint and your current state, there's no point in, like, say, just reverting back to the checkpoint won't help because the environment itself has changed, right? Now, restarting from a safe checkpoint with all other parameters constant will only help you get past, say, random hardware failures or flakes. But if it's a deterministic issue, it won't really help. Like, if you are running into out-of-memory errors at step 256 and do a revert to step 250, you will still run into an error on step 256, right? Unless you have taken some corrective measure. Now, for this, you need to restart with a change in parameters or a change in configuration or some change so that the conditions that led to the initial failure do not exist anymore. Now, this is where a major challenge lies in the monitoring space, and this is where something that we call forking can help. The problem with resuming runs in most common experiment trackers is you are actually starting a new run. That for the experiment tracker, when you resume a run, when you say fork a run or you restart a run, it basically becomes a new run, right? And not a continuation of the same run. However, like, what you actually want to do is continue the same run. Now, the visualization becomes all jumbled, and you have to tell anyone seeing the chart that the visualizations or the plots that you see are actually the same run and not, like, say, different runs. So, for example, if we have your experiment progressing, your loss gradually decreasing, which is generally should be the case. And at this point, maybe there is any error, but could be anything, right? Now, there are, say, four scenarios possible. The basic, you don't have any checkpointing, nothing, so you don't really have an option. You have to restart from scratch, restart from step zero. So you restart, run your experiment again, and maybe it fails at the step again, maybe it does not, it continues, or maybe it fails somewhere else. Now, the second step, the second scenario is maybe you have checkpointing and your last checkpoint was maybe at this step here. So you restart from the same checkpoint. So your loss value at that checkpoint was this. But when you restart your experiment, so like you were mentioning, it starts again from step zero. Right, so you get another parallel, say, graph. Now, it's supposed to be a continuation of the same graph, right? But it does not look that way because it starts from step zero. Now, in some monitoring tools, you can actually specify the step you want the experiment to start in. So what you could do is, say, start from the next step of the failure, or the next step from the step where you had the checkpoint. So, example, you restart it from here. And then you could have, say, multiple such restarts. So one restart from here, and this and restarted here, and so on and so forth. You can ignore that the losses are increasing here. Now, this is still better than, say, the previous scenario because it gives you an idea of the direction your experiment is progressing. You can, like, say, figure out, okay, so this experiment happened after this happened after this. So you have some idea of lineage. But this can quickly become very complicated. So it could look something like this because you could have multiple restarts from different steps of an experiment, right? So for example, if it looks something like this has been started multiple times. Here's another fork. Now, in getting a view of the inheritance becomes a bit problematic because now you don't know if this experiment, like this one you see here, yeah, if this one originates from this point, or it originates from here, or it originates from here, you don't have an idea. So what you what you should ideally have is a way of being able to link the child runs with the parent run at the point where they were forked. So it would look something like this. What you have done here is just basically like link the runs together at the forking point. And now it's pretty easy for you to go from the end of one child run to the initial history. So if you want to get the history of this run, so you can easily trace the lineage all the way back to the parent run. So you have a point, you have a failure at that point, and you restart a checkpoint. You basically create a fork, and then you have, say, multiple forks, as you can see. Like, you have different forks, but it's difficult to know which child run originated from which parent and at which step. So what you do is you just turn on inherited metrics, and this creates a link, inheritance between all the runs. So now it's much easier for you to visualize the entire experiment, the entire, say, experiment from each children to each of the parents. This now brings us to the second main issue when it comes to, say, monitoring large scale training, right? How do you visualize and compare the data which is involved, the large volume of data involved in training such a large scale models? The first challenge is organizing your experiment data. So as Neil from Wabi says, the ML teams at Wabi were continuously running large scale experiments with ML models. And one of the significant challenges they faced was keeping track of the data collected from experiments and exporting it in an organized and shareable way. Now, this brings us to the, say, single source of truth, say, principle that we had discussed earlier. So as Patrick from DeepSense says, they trained more than 120,000 different models for more than 7,000 sub-problems identified by different combination of features. And what they did was stored a lot of metadata, visualization, say, hyperparameters, predictions, models, etc., in the same dashboard. So you have that one dashboard that gives you the complete overview of the problem. Now, this problem of organizing experiment data is not limited to training at scale, but it's definitely, say, amplified by it. So when you're training at, say, small scale, you can use, say, tools like MLflow, TensorBoard, and use it to compare, say, 10, 20 different experiments. But what do you do if you have to compare 200 experiments or, say, 2,000 experiments? MLflow does not really scale that well. The solution, as discussed already, a single source of truth that scales according to your experiment. So it does not really matter if you are logging 2 experiments or 20 or 2,000 or 20,000. No. Yeah. So this is a sample dashboard of what you see at Neptune, and a lot of other experiment trackers also have similar dashboards, and it's completely customizable. So you have your loss curves, you have metrics, you have a sample of a data set, you have your hyperparameters, the previous memory and GPU utilization graphs you saw, you could add them as well. So it gives you like an overview of everything you need to see in an experiment in one single place. So it's just a single URL. Anyone who wants to see how that experiment progresses just goes to that URL and sees an overview of that experiment. Now, there are multiple advantages of using something like this. So as Lucas says, you just create it once, and as and when you create multiple experiments, they can use the same dashboard template. The only thing that changes are the values based on that particular experiment. Now, this is also much more intuitive than, like, say, checking your CloudWatch logs, right? And it enables even non-technical people to kind of make sense of how the experiment has progressed. So it's easier for you to like just read the best values of the metrics in this dashboard in the like nice color coded way than having to find the relevant values in CloudWatch logs. And finally, but I think the most importantly, it also helps you visualize custom metrics. So custom metrics are the metrics that you're not explicitly logging from your source code, right? So for example, like say if you have already logged precision and recall, and now you realize that maybe the fun score would have been a better metric. You have a couple of options. What you can do is download the metrics from the tracker, calculate the fun score in Excel, and you may or may not be able to log it back to the tracker or the monitoring tool. Now, if you're not able to log it back, that creates a problem because now you don't have a single source of truth anymore. All your experimentation is being logged to the tracker, but your F1 scores are in that Excel that you manually need to update. If you are able to log it back, well and good, but then it again involves a manual step of being able to of having to calculate it offline and then logging it back. Uh, the other option is like you rerun the experiments and now log the F1 score as well. However, there are a couple of assumptions here. So one is again you're assuming that your experimentation environment is constant; it has not really changed. Uh, yeah. Now imagine doing any of the above two solutions for like say anytime there's another change, or like say for say 200 experiments. It is not really sustainable and can quickly get out of hand. So a solution for this is being able to like say log only the basic metrics, like say only the precision and recall, and calculate everything in the tracking tool itself. So you just enter a formula that you want to calculate. So for F1 score, you enter a custom formula. You have precision and recall already logged, and for each experiment, the tracker will like say compute the F1 scores for you. And this solution is really scalable because you just have to like say enter the custom formula once, and then for each experiment you have like all your custom metrics already like shown to you by the tracker itself. So irrespective of the number of experiments, you just do it once, and the formula and the custom metric is now shown for the previous runs and also the next runs that you will be logging to the experiment. Now, as an added bonus, this also minimizes your logging calls because now you're not, say, logging 10 different metrics. You're only logging 2 basic metrics, and all other, say, metrics are calculated at the experiment tracker itself. So this can also, like, say, fasten your training slightly. And then this is kind of a niche challenge if you want to, like, say, visualize large embeddings. So my friend Prince was trained the world's first Llama 3 with say 6 billion parameters. And while doing that, he ran into this challenge of not being able to visualize large size embeddings. So he was extracting 1 billion tokens from a large data set, but there was no way to like visualize the relationship between these tokens. Yeah. There are couple of like kind of workarounds that you could use. One of them was used by Hugging Face for their fine web data sets. That paper is also being presented at NeurIPS. So what they have done is on the graph at the left, it basically like shows, yeah, it shows the topic distribution between the fine web and the fine web education data sets. So the fine web data set consists of around say 5.4 trillion tokens, and the fine web education data set contains around say 1.3 trillion tokens. Now, creating this topic association, topic distribution is relatively easy if you have a smaller size database. But for say larger, say trillion sized databases, what you need to do is you first need to extract the topics themselves. This is a challenge if you don't have access to, like, say, Hugging Face level of infrastructure. And secondly, you need, like, say, serious hardware to just being able to, like, say, compute these associations, right? Now, I came across two kind of tools that handle this a bit better. So one is Deep Scatter. I had a video here, but I would rather just show it. You are seeing 20 billion biomedical extracts being visualized on uh, or in the same cluster. So you can, like, access each of them, and if I zoom in, you can access each individual paper, and clicking on them takes you to that relevant paper link. So this is one solution, and the other is Jupyter Stacker, which is a bit more user friendly for, say, data scientists and ML engineers, because it, like, integrates directly with Jupyter notebooks. You can use it in Jupyter notebooks itself. It's not as scalable as Deep Scatter, but I mean, you don't have to, like, say, worry about Node.js or learn JavaScript. Cool. And finally, like, say, live monitoring can also help you uncover issues in your data pre-processing. So for example, the team at Mosaic ML mentioned that if you see loss curves like these, they call these wavy boys. If you see loss curves like these generally indicate a problem in a data set shuffling. So in case you are seeing something like these in your experiments, might be worthwhile to take a look in how your data sets are being shuffled. Cool. This brings us to the final group of, or the final pain point in reproducibility and transparency. So these have always been an issue in academia and are and are, like, say, increasingly being an issue in industry. So much so that it phenomenon has a Wikipedia page and a website dedicated to hosting papers that cannot be reproduced. I hope none of your papers land there. So for your experiments to be reproducible, first your experiment has to be, as highlighted by Davis, uh, first your environment has to be reproducible, as highlighted by Davis. And this is honestly a pretty tall ask in the Python ecosystem, because unless your requirements are pinned, any change in any of the dependencies can throw your entire experimentation or entire, say, pipeline haywire, right? So you're checking for, say, different torch versions, monkey patching, different functions. Now, you also have other moving parts, like, say, for example, data sets, right? So like, as Neil from Wabi mentioned, you have to, like, share benchmark results in a constant place and retain data for later comparison. Now, to be able to reproduce experiments, you need to have a record of the entire experiment setup and also the experiment results. So if you don't have a record of the experiment results, there is no way for you to validate if that experiment has been successfully reproduced, right? So some of the challenges, like, say, faced by Respo Vision was, one, debugging issues. So Respo Vision actually works on computer vision and machine learning for sports data. They work mostly on, say, 3D data. So lack of transparency into pipeline runs leads to issues when debugging and comparing experiment results. And since there was no proper tracking, reproducing good experiments is a pain, because then they have to figure out the data set and the parameters that they had used for the experiment in the first place. Yeah. So based on, say, what we have discussed, we need the following things to make an experiment completely reproducible. So first, we need the hardware details. You need to know, like, what hardware the experiment was running on. So for example, the number of GPUs, number of CPU cores, these days even the make of the GPU, right? The capacity of the memory capacity, so on and so forth. Then you need information about the environment, the operating system, hopefully not Windows, the software versions, the package versions of each Python dependency that you have used, the version of Python. Yeah, see, this is why you don't use Windows. Yeah. Then you need details around the data set, source code, configuration and parameters, the model artifacts, binaries and weights, and finally the output data. Right. So, but how is this, say, different in hyperscale? So for small scale experiments, you can get away with having almost everything tracked on a Jupyter notebook. But for larger scale, you use dedicated tools for each of these components. So for example, Git works for source code, maybe DVC for dataset versioning, S3 for uploading model artifacts. Now, all of this metadata can be added to the notebook that you are using. But in hyperscale, training will be split across different experiments or forks of the same experiment. In some cases, it would be possible for you to get these details of all parent runs in an experiment. But how do you do that? You cannot have 100 different Jupyter notebooks if you have 100 different folks, right? And even if you did, how do you track the lineage? So what you need is a tool that lets you associate all the relevant metadata of an experiment, say for example, source code, parameters, data sets for an experiment in a single place. So this also ties back to the say single source of truth principle that we had previously discussed, and saves time in analysis and trying to reproduce your results. Some other unsolved challenges that we found. One was like say debugging deep learning accuracy. So why do say models behave the way they behave? So as again Davis from Mosaic ML mentioned, debugging deep learning accuracy is one of the most difficult challenges in computer vision. In all of computer science currently. And if any of you are working on solving that challenge, it will be like we would love to hear from you.